Hello, everyone. Welcome back to MP Coding. Today, we will write our first character device driver. In the previous video, I covered the basics of Linux device files, including their types and how to interact with them. If you are new to this series, please watch the previous video first. It provides essential background on device files in Linux. To begin, copy the folder from our first Hello kernel module. Paste it into this character device driver folder. Rename the folder to 01 My First udev. Rename this source file to my udev as well. In Makefile, update this to my udev object file. The setup is now ready for build. Let's start coding our character device. Open the source file and first, update the module description to our first character device. We need to include the Linux file system header for file operations. Add hashtag include linux/fs.h. This header provides structures and functions for handling device file interactions. In the device initialization function, we need to register the character device. For that, here we have this register_chr dev function. This function requires three parameters: the major number, the device name, and the file_operation structure pointer. First, let's declare the file_operation structure at the top of the file. Static struct file_operations, I will name it fops. Then pass an empty structure for now. The file operation structure contains function pointers for Linux file operations, such as read, write, and open, release. In this video, we will not implement any of these functions. In the next videos, we will add them with examples. For now, the empty structure is fine. The kernel uses default behaviors for unimplemented operations. Here in the register_chr dev function, pass 0 for the major number. I will explain what this means in just a minute. Then, pass the name for our device. I will pass my_cdev. Finally, pass the address of the file operation structure. Let's look at what passing 0 to the major number means. Here, in the Linux kernel module programming guide book, under the character device driver section, we can see this detail. If we pass a major number of 0, the function returns the dynamically allocated major number. This approach avoids conflicts with other devices, as the kernel assigns an unused number automatically. So, declare a static int major variable to store the return value from this. And I will add this device name to a char pointer, so declare a static const char pointer for the device name. Use this at the top of the file, after the includes. Static const char pointer, my_device equal to my_cdev. Pass that my device variable here. If the major number is less than 0, it means registration failed. The kernel did not allocate a dynamic major number. Instead, it returned an error code. Here let's print the error, character device registration failed. Then return the major as error code. Remove this last print statement also to add a new one. Finally, print this information to confirm success. Character device registered, major number. Pass the device name and major number as arguments. This formats the output correctly and lets us verify the assigned major number in the kernel log. The init function is now complete. Let's edit the exit function. Since we registered the character device, we need to unregister it to clean up resources properly. We have this function call unregister_chr dev and need to pass the major number and the device name as arguments. We have now completed the simple character device registration implementation. Finally, edit the goodbye kernel message in the exit function also. Okay, let's build the module. First, navigate to the source directory. Then type make and hit enter. You can see build complete successfully with no errors. Now, let's load the module. Before that, open a new terminal to monitor the kernel messages. In that terminal, type dmesc-W and press enter. This displays the kernel ring buffer messages and follows new entries in real time, so we can see the output from our print statements. Let's load the module. Type sudo insmod my_cdev ko and press enter. The module loads successfully. In the D message output, you can see the confirmation message with the assigned major number of 236. This major number is dynamically allocated by the kernel as we pass 0 during registration. Now, verify the registration. Type cat/proc/devices and press enter. This file lists all registered devices in the system. Look for the character devices section. You should see my_cdev listed with the major number 236. If we look in the /dev directory, we cannot find a new device named my_cdev. That is because we only registered the device number with the kernel. We did not create the corresponding device node. Here, to make the device accessible from user space, we need to create a device node manually. As we discussed in the last video, use the mknod command for this. Give the destination and name for the new node. I will put it in dev directory and give the name as my_cdev. The C specifies a character device. The major number is 236, which the kernel assigned dynamically. The minor number is 0. We use 0 because this major number supports only one device instance. Now, look at the dev directory. You can see the new device node called my_cdev. To verify the node, type ls-lh/dev/my_cdev and press enter. The output shows the node as a character special file with the correct major and minor numbers, along with default permissions. Now, this device node allows user space applications to interact with our driver through standard file operations. In the upcoming videos, I will also discuss file operations. For now, let's continue with empty file operations. Now, unload the module. Type sudo rm mod my_dev and press enter. This removes the character device from the kernel's module list. Now if we open the /proc/devices file, the my_dev entry no longer appears in the character devices section. This confirms the device was properly unregistered and the resource is released. Let's define a static major number in the code. At the top of the file, after the includes, add this macro, define my_major64. Replace the 0 with my major macro. Major numbers from 64 to 127 are reserved for local or experimental drivers. This avoids conflicts with standard devices. The registration function now returns a status code, not the major number. On success, it returns 0. On failure, it returns a negative error code. So remove the static int major variable. Declare a local int status variable and store the return value from registration. If it's not 0, print the error message. Update return to status. Change this to my major macro. Now, update the exit function for the unregister call. Change this to my major macro. Okay, the code is ready. Type make and press enter. The build completes successfully with no errors. Before loading the module, let's view the currently registered devices. Type cat/proc/devices and press enter. In the devices list, we can see no devices registered under major number 64. This confirms the number is available for our driver. Let's load the module. Type sudo insmod my_cdev ko hit enter. In the D message console, you can see the confirmation message. Let's check the registered devices. In the character devices section, you can see my_cdev listed under major number 64. This confirms the device is now registered with the kernel. Let's unload the module. In the D message output, you can see the confirmation module unloaded. If we check the registered devices again, the my_dev entry no longer appears under major number 64. This confirms the device was unregistered successfully. Let's demonstrate what happens when we try to register a major number that is already in use. Major number 89 is assigned to the I2C bus driver in Linux, so it is reserved and occupied by the kernel. Save the file and rebuild the module. Type make and press enter. Now, attempt to load the module. Type sudo insmod my_cdev ko and press enter. The load fails. The terminal shows an error. Device or resource busy. This occurs because the kernel detects the major number is already registered and rejects the request to prevent conflicts. This highlights the importance of choosing an available major number, especially for static assignments. This register_chr_dev function is a legacy method. It is simple but outdated. For modern drivers, use alloc_chr_dev_region instead. This function is more flexible and follows best practices. It allocates a range of major and minor numbers dynamically, but does not register the file operations directly. If we search for function definitions on bootlen, here the fs.h file and function implementation is here in the char_dev.c file. Make sure to select the correct kernel version. In the function definition, we can see these parameters. The first parameter is an output dev_t pointer. It receives the first assigned device number, which combines the major and base minor. The second parameter is the requested base minor number. It specifies the starting minor for the range. The third parameter is the count. It sets the number of consecutive minor numbers to allocate. The fourth parameter is the device name. It registers the name with the kernel for identification. Now, let's implement the modern approach. Replace register_chr_dev with this new function. Now, remove the myMajor macro. We no longer need it. Declare a static dev_t variable to store the device number. Name it dev_nr and place it at the top of the file. This global variable holds the allocated device number, which includes both major and minor components. Pass it here as a reference. The second parameter is the base minor number. Pass 0 here. This starts the allocation at minor 0. In this example, we need only one device, so the count parameter is 1. This allocates a single minor number for our device. Finally, pass the device name as the last parameter, my_device. Here, for the third parameter, the count of minor numbers required. In a professional implementation, pass minor mass plus 1. This allocates the full range of minor numbers for the major, which is the standard approach. In future videos, I will cover this in more detail. For the next implementations, add the include file linux/cdevh. This header defines the struct dev and functions such as dev_init and dev_add. These are required for the modern character device registration. Now, let's implement cdev_init. We need to pass the dev structure and the file_operation structure as pointers to dev_init. This function sets the file_operations pointer within the dev structure. Let's create the cdev structure. At the top of the file, after the device number, add static struct dev my_cdev. Pass this my_dev structure to the dev_init function as a reference. The second parameter is the file_operation structure, passed fops as a reference. Now, set the owner for the character device in the my_cdev structure. Use this underscore module for this. This macro points to the current module. It prevents the module from unloading while the device is open, which protects against use-after-free errors. Now, we need to add the my_dev to the kernel's device list. Use the dev_add function for this. This takes 3 parameters. The first is a pointer to the dev structure, so pass reference of my_cdev. The second is the dev_t device number, which is dev_nr. The third is the count of minor numbers, which is this for single device. The cdev_add function returns a status for the addition. So store that return value in the status variable. If the status is not 0, an error occurred. Print an error message. Error adding cdev. And return status as the error code. Here, we no longer have the myMajor macro. To get the major number from dev_nr, use the major macro for this. Pass dev_nr to it, and it returns the major number. The same applies for the minor number with the minor macro. Here, add this to show the minor number in the message as well. I forgot to add the cleanup for the allocated region. If an error occurs during dev_add, it is necessary to release the device numbers. After the error print, add this line: unregister chr dev region, pass dev_nr and the minor count. Copy this line. We also need to add it in the exit function for proper cleanup. Remove the previous unregister_chr dev call from the exit function. Replace it with the new cleanup sequence. Here, in the exit function, need to remove that dev structure from the kernel's device list. To do that, add the cdev_del function, del stand for delete, and pass the reference to my_cdev. Okay, that completes the registration of the device to the kernel's device list. Quick recap: what we did: first allocate the device number region, then initialize the file operations in the dev structure, and finally add that device to the kernel's device list. In the exit function, first delete the device. Then, unregister the character device region. Now, let's build the module to see it in action. Type make and press enter. The build completes successfully with no errors. Before loading the module, open a new terminal to monitor the message. Okay, let's load the module. Type sudo insmod my_cdev ko and hit enter. In the D message output, you can see that the module loads successfully. The kernel dynamically allocates the major number 236. If we check the devices list, in the character devices section, you can see my_dev added, with the dynamically allocated major number 236. This confirms the registration succeeded. Let's remove the module. In the D message output, you can see the confirmation. Still, we need to manually create this device node in user space using the sudo mknod command, passing the destination, name, device type, major minor numbers. This manual process is pretty messy. We must create the device node every time the module loads. How these other devices appear automatically during system boot. There is a subsystem called udev. It handles the dynamic creation of device nodes. So, let's look at how to implement automatic device node creation. To create the node in user space without manual nod, use the device_create function from the kernel's device model. It takes 5 parameters: the class pointer, parent device, the dev_t number, driver data, and a format string for the device name. If we open our reference bootlin site and search for device_create, we can find the function definition here in the core.c file. You can read this definition to get an idea. I always recommend reading the function definitions yourself. It's good practice to search for them on your own. And this function returns a pointer to the device structure. Okay, let's implement device_create now. Before that, we need to create a class structure. For this, we use the class_create function. If we search for class_create in bootlin, we see the function definition. This function takes just one parameter, name for the class. It returns a pointer to the class structure on success. If it fails, the return value is an error pointer. Okay, let's add a global struct class pointer to store the return value from class_create. Declare it at the top of the file, static struct class pointer. I will name it my_class. Okay, save the return value from class_create in the my_class pointer. Then, pass the name for the class as a string. I will name it just my class. Here, if the my_class pointer indicates an error, let's print the error message. Could not create class my_class. As return value, let's return -1 to indicate the error. Before returning, we need to perform cleanup. Actually, we need these two, so copy that and paste it here. Now we are repeating these two unregister functions. To avoid this duplication, I'll add a goto statement to jump to a shared cleanup section. For freeing the device number region, I'll jump to a label called free_device_nr. Then, I'll copy the unregister function, paste it into here, free device number section, and finally return the status. Then, for deleting the cdev, we can do the same. Create a new label above the free_device_nar label. Name it as delete_cdev. Then copy this and paste it here. Now remove these lines and add go to delete_cdev section. Here change the status to error no memory. Later, I will show how to return an error code properly. Here add, go to the free_device_nar section. Now we don't need this return, remove that. When we call go to free_device_nar, code jump to this section, skipping others. Same for here, when we call go to delete_cdev section, it runs all of these codes under the label. Okay, now let's implement device_create. This function returns a pointer to the device structure on success. If the return null pointer, it indicates an error. So let's print the error message here. Now, we need to pass the parameters to the device_create function. The first parameter is the my_class pointer. The second is null. We do not have a parent device. The third is the device number, dev_nar. The fourth is null again. We are not passing any driver data for callbacks. The fifth is the device name format string. Use my_cdev here. This final two parameters work together to form the device name. The fifth parameter is a format string, like my_dev%d. This acts as a template. The sixth parameter is the value to insert, such as 0. The %d placeholder gets replaced by this integer. Together, they generate the name my_cdev0. This appears as the node in /dev and sysfs. If device creation returns null pointer, let's print error message, could not create device my_cdev0. Set status to memory error, and then let's jump to new section called delete_class. Under the delete_class label, we need to clean up the class allocation. Add class_destroy function and pass the my_class pointer. Here, this function frees the class structure and its resources. Copy this class destroy function. We need call it in the exit class also, so paste it here. In addition, here we have created the device using device_create. In the exit function, we need to clean it up as well. So call device_destroy and pass the class and the device number. This removes the device entry from sysfs and notifies udev to delete the dev/my_cdev0 node. Finally, in the init function, add more information to confirm success. Print this message, created device number /sys/class/my_class. And add one more, print, created new device node /dev/my_cdev. This should be my_cdev0, not device 0. Okay, we have completed the implementation. Let's build the module now. Before loading the module, let me show you the /dev directory. You can see there is no my_dev0 node here yet. I forgot to mention earlier, I have removed the previous my_dev node that we created in the first part of the video. If you do not remove it manually, it will remain there. This is because we did not call any remove function in previous examples. If it is still there, remove it now. Run sudo rm/dev/my_cdev. Here, I have opened another terminal to monitor the udev console messages. First one, open the D message buffer. Type udev adm monitor and press enter. This command monitors udev events in real time. You will see kernel and user space messages as devices are added or removed. Okay, let's load the module. Type sudo insmod my_cdev and hit enter. Here, you can see the module loaded successfully. In the D message output, the confirmation message appears with the allocated major number. In the udev monitor terminal, you can see the kernel event for the device add. This triggers udev to create the /dev/my_dev0 node automatically. Now, let's look at the /dev directory. You can see that the my_c_dev0 node has been added. This confirms udev created it automatically from the device_create call. It was created under major number 236 and minor number 0. Now, let's check the device list. Type cat/proc/devices and press enter. Here you can see my_cdev listed in the character devices section under the dynamically allocated major number 236. Now, let's check the /sys/class directory. Type ls/sys/class and press enter. You can see the new my_class entry listed there. This confirms the class was created successfully in sysfs. Now, let's look at the my_class directory. You can see the my_cdev0 entry here. This confirms the device was added to sysfs. This my_cdev0 name comes from the string formatting we set when creating the device. The 0 at the end is from the integer parameter we passed to device_create. Let's unload the module. Type sudo rmod my_cdev and press enter. You can see that the module unloaded successfully. The D message output and udev monitor confirm this. Let's check /dev directory. My_cdev0 is removed successfully. If we check the /sys/class directory, we can see that my_class has also been removed. If we check the /proc/devices list, my_dev has been removed from the character device list also. This confirms that the entire cleanup process completed successfully, meaning we no longer need to manually create or remove the device node. udev takes care of that automatically. This is how a character device is created with udev. In this video, we covered character device creation, major and minor number allocation, the use of dev_init and dev_add, and udev's automatic device node handling. In the next video, I will explore file operations in more detail. Like and subscribe. See you in the next video.